All right, let's start looking at this problem called number of good paths. So in this problem, what's given to us is we are given a tree, and we are for each node we are given a specific value through this values array, and the tree is represented through this list of edges. Ultimately, from this information, you can build the tree. And you have to find the number of good paths. Now, how is a good path defined? Well, the good path is a path which starts and ends with nodes having same value. So the starting node and the ending node have a same value, and all the nodes in between have values lesser than the endpoints, right? So that is a good path. So for example, in this case, the values marked in blue are the actual values. So one thing obviously is each individual node is a good path because it starts with the same node and with the same node. So the starting and ending node have the same values because it's essentially the same node and there is no intermediate node. So how many of our nodes are there? Those are all considered good paths. But if you want to find paths which have more than one node, then you'll have to find first two nodes with the same value, right? Because the starting point and the end point have the same value. So in this case, we can see these two nodes have the same value as 1. So you might try out this path 1, 2, 1, but this is not a good path. The reason it is not a good path is because the intermediate node has a value greater, and the definition of good path is that your starting node and ending node that have same value, and all the intermediate nodes have values lesser than or equal to the starting nodes, which is not the case here. Are there any two nodes with the same value? There is this 3 and this 3. So both these threes have the same value. So what are the intermediate nodes? Well, 3, 1, 2, 3. Well, this is a good path because the intermediate nodes have values lesser than the starting and end nodes. So this is a good path. So in this case, all individual nodes plus this path was a good path. This is another example, 1, 1, 2, 2, 3. Well, all individual nodes, and then these two ones, but there is no intermediate node, all good. And these two twos, again, no intermediate nodes, so all good. So this is good enough. So now how can we solve it? Let's look at maybe some more examples and then try to come up with an approach. So I'm gonna build some random tree, and let's say I directly use the values when I build the tree. So let's say some random tree, we have a 1, we have a 2, a 3, a 2 again, a 4, a 3, let's say a 4 here, let's say a 2 here, let's say a 5, a 4. Okay, let's say this is our tree, right? And now we have to find out how many good paths are there. Well, obviously the number of nodes that are there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 obviously are the single nodes. Other than that, we would want to find out for each and every value, are there nodes with the same value? So for example, if I look at 1, well, there is only a single node with one value, so I'm not going to find anything. Then I'll look at 2. So there are these different 2s that are there. I have a 2 here, I have a 2 here, I have a 2 here, right? Now can I connect these three 2s somehow individually to taking 2 at a time and see if I get a good path? So if I look at these 2s, this path, it is not a good path because a 3, which is a greater, comes in between. Okay, what about this one? Again, the same thing. This 3 is causing problem. And what about these? Well, there are multiple 3s in the path, and that breaks the condition of good path. So for 2, there isn't any good 2 nodes that I can use at the ending points. What about 3? There are two 3s, yes, this 3 and this 3. And so I can join, yeah, this path is a good path, so this can be considered. All right. What about 4s? Well, there are a bunch of 4s. 1, 2, 3, 4. So I can choose any two of them using 4C2, right? So which is, so there are 6 different ways in choosing any of these two. Let's look at some random ones. So if I look at this, yes, this is a good path. What else? If I look at this, this is also a good path. What about this? This is also a good path. But this is not because of this 5. Again, this is not because of this 5. This is not because of this 5. So the problem, your paths cannot be considered if there is a node which is bigger. Any node through between the two endpoints, any node between these two nodes, if any of the node is bigger, it causes a problem. So we have to essentially break this here. Now, how do we break it? That's the thing, right? So let's look at this. So essentially, the point is for any value that I'm considering, any node which is greater than that value is a problem for me. I don't really want to consider it. So why not just do it that way? What I mean by that, all right. So how about I look at each and every value and I only consider the nodes which are lesser than or equal to the in value with that. So when I look at one, the only node that I'm going to consider is just this one node because there is no other node which has a value less than or equal to one, right? So that's the only node I consider. And now let's try to find out the number of good paths for this. So the number of good paths is there is a single node, so the number of good paths with one, I'm going to only get one, right? Now let's do two. So for two, I'm going to consider only the nodes which whose value is two or lesser. So basically, I can just add a two to this. So I build a tree by value. So initially, my initial node is one. That's my only value. Then now I add the two nodes. So I can add this two. I can add. There are other twos, but I cannot add threes. So I will have to consider these two separately, and I will have to consider this two separately as well. So this is the entire, now you can call it forest, right? That we are considering. Now within this, how many different good paths that I can find from twos? This, so essentially now you have to look at different sets or different connected components, right? If I were to tell you, if I were to tell you there is a tree and you don't have to consider good paths, you just have to tell me if in a tree or if in a connected component, a tree is a connected component, right? If there are X nodes with value 2, how many different paths will be there with endpoints as 2, right? So if there are X nodes, then there are either I choose any one of them individually, so X is C1, right? So essentially just X. So each of them individual nodes is a good path or is a path, plus choosing any two of them, right? Because there is always a connect, because it's a connected component, so there's always a connection between any two nodes. So plus X is C2, right? So given any connected component, right? Given any connected component, the number of paths are x plus xc2, right? Or simply xc1 plus xc2. Either you take just one node or you take any two of them, and all the different combinations of taking any two can be considered, right? So in this case, we'll do that for each and every component individually. So there are three different components. Each component has one, one, two. Because there are only one, one, twos, there is no option to choose two twos because these are not connected, right? So within a connected component, so within this, how many paths with the starting and ending node as two? Within this, how many paths with the starting and ending node as two? And within this, how many nodes with the starting and ending node as two? Well, that's each will give one answer. So for total two, oops. So for nodes with value two, I get total three different paths. Now let's move to three. So how can we do three now? So we just add all the three nodes. There are two of them. So let's add this three node and add this three node. And again ask the same question. How many connected components are there? Well, now there is a single connected component. How many three nodes are there? There are two of them, right? So how many different good paths can be there? Well, it will be either you take any one of them or you take any two of them. Oops, not three. If you so there are three nodes. So either you take any one of them or you take any two of them, right? So how many paths are there? Two plus one, three. So there are three total good paths to be considered for three. Just this node alone, just this node alone, or this path, right? Now let's do four. So if we add all the four nodes, we will add this, we will add this, we will add this, and for the this four, I'll have to add it separately because I cannot add this five yet. So now how many connected components are there? There are two, right? So the first connected component, so there are two connected components. One of the connected components has just a single four, so that will just give me one path, and the other one has one, two, three different connected components, three different nodes. So there I have option to either do take any one of them or take any two of them, right? So this is three, all these individual nodes. or if you take any two of them at any given point in time, because within this, all the three paths work. This 4 to this 4 works, this 4 to this 4 works, and this 4 to this 4 works as well. So all those three work. All right, so this we get 3 plus 3 is 6, and this from this separate connected component we get one more, so 7. So for 4 we get 7 different good paths. And now let's finally do 5. So now you add 5 here. Number of connected components is 1. Within that connected component there is just a 1 5. So for 5, because there's only single 5 node, so this is your total. You can just add them up, and that's how your total number of good paths are there. So that's the logic, right? Essentially, what we are doing is we are starting from the smallest value till the largest value. And for each value, we are adding those nodes into our tree. And how are we doing that? And also, when we are doing that, we have to be careful. Like, for example, when we added this 4, this 5 wasn't added yet. Similarly, when we added these different 2's, we had to add them separately because we could not add them as a connected component. So we have to keep connected components. And so for this approach, we are going to use the union find data structure. What we are going to do is initially each and every node is an individual node, right? So if there are n nodes, each of them are n distinct sets to begin with. And then we start considering different values. So now I'm considering value v. So all nodes with this value are what I'm going to consider, right? And what I'm going to do is that how do I add it into the connected component? Well, there are, for each of those nodes, look at its neighbors. And if the neighbor is already considered, which is mean if the neighbor value is less than or equal to well, then join them, right? That's it. And that is the way I'm going to only consider nodes less than or less than or equal to the current node's value. And based on this, I'll find out how many different connected components are there. And for each connected component, I'll find out how many different good paths that we can form. So that's a general idea. Let's come to the code and see how we can actually implement this. All right. So first things first, let's build the basic tree structure, right? So let's look at what the different inputs are given to us, and we want to build a data. So let's build the adjacency list based representation of the tree. So we go list of integer. Let's call it the adjacency list equals to new array list, and then we are going to do for each node. So for each I equals to 0, I less than length, I plus plus. We want to add a new an empty adjacency list. So adjacency list dot add new array list. Now actually add these neighbors based on the edges array. So for each edge in the edges array, let's get the two nodes. So a node is u is edge of 0 and v is edge of 1. Let's join them together. So adjacency list of u, we add v. So we add v as a neighbor of u, and we add u as a neighbor of v, both of them. So that's good. That's our tree representation. What else do we want? So we said that we want to consider all nodes starting from first we want to consider all nodes with value 1, then we want to consider all nodes with value 2, and obviously there are distinct values, so we just want to consider each and every value. So we want to basically we want a mapping for each value, what are all the different nodes. So we want a mapping from value to list of nodes which have that value, and we want to start with the smallest value to the largest value. So that means this val have to be sorted. So I want a sorted data structure based on values, based on the key which have this list of array, right? So what can we do? We can have a map, but a tree map, which will keep the values in sorted fashion. So integer is the values and a list of nodes. So a list of integer will have the value. So this is values to nodes map, right? Or we can just call value to nodes. Okay, this is good. Values to nodes map, and we build this as a new tree map. And so how do we set it up? So we go through each and every node. So for each, so int I equals to 0, I less than length, I plus plus. So val equals to vals of I. If now if the node is not if the key is not already added into the map, let's add it. So if this key is not present yet, then let's add an empty list. So put val new list, and now we already have a list corresponding to this value. So we'll add each and every node which have that value within it. So value dot nodes map dot well, in this we will add this index, right? So based on this, we have now for each value, starting from the smallest value to the largest value, we have the list of nodes that are there. Now we'll build our connected component or the union find or the tree starting from the smallest value to the largest value. So we're gonna do this union find. So let's also implement union find data structure separately. So let's have a separate class for that. So let's say we have a union find data structure which takes in, it will have n different nodes. All right. So do we want to do the union find first, or we'll implement the union find at the end? First, let's build the basic logic for our code. So now what we're saying is let's assume we'll have a union find data structure. So let's assume we have a union find data structure which can have and nodes. So each of them are initially considered as individual sets. And now, so we go through each and every value. So for each value in this value map, so we are going to the smallest to the largest value. So we are going to the smallest value first. And we want to do is we want to go through each and every node in that, right? So for each node in corresponding to this value. Now we're looking at each and every node, and we will add that, we'll add edges if they are, for we'll go through their neighbors. So for each neighbor in the adjacency list of this node, we will connect only if the neighbor is lesser than or equal to my value. So if value of neighbor is lesser than or equal to my value, which you can also do else or you already know the value as well, right? If that's the case, then you want to be able to do union on the neighbor and myself, right? Otherwise, you don't, because you only want to connect the nodes if they are if the one of the nodes if the neighbor is of the smaller or equal value, and we keep doing that. So for each value we do that. So we've gone through for each value we have gone through each and every node, and we have added relevant edges that could be added, and if there couldn't be added any relevant edges, then those they remain as individual separate connected component. Now we want to find out how many different connected components are there which contain uh, a node with this value, right? That's our job to find. So let's add a mapping from connected component to the number of nodes that each connected component has. So let's say we build a map So we want a component to number of nodes with value as well. That is what we want. So let's build a map from integer. And so how do we do that? So we are interested, we'll again go through each node, right? So we go through each of the node which actually has the same value. And now what we do is we find their, for each node we find their component, which component they are part of. I wanna fix the formatting a little bit. All right. So component, you'll do find their component. So the union find will give their component. So you get the component of this node. And now what we're going to do is map dot put component. You will increment, right? So map dot get a default. So in this component, you're going to add the number of nodes with the value. So now this map contains all the different components and which have this value and how many of these are there. So now for each component, or each subtree, or each set, or each connected set, whatever you want to call it, right? So we are looking at each of them in this map, and we get this number of nodes, right? Uh, which is a so component dot get, well, what we are not map dot get component. So this component has these many nodes of these many interesting nodes, right? Let's call it just n. So now what do you want to do? Well, let's maintain the total good path somewhere. So let's say we have this good paths is 0, and we'll increment these good paths based on nodes with this value. So, well, first is paths with single endpoint. Then you just do good paths plus equals to n. All of these nodes, right, are individually can be considered, or you want to consider paths with two endpoints. For that, you will do nc2, right? So good paths plus equals to n minus 1 by 2. So you do n times n minus 1 by 2. And obviously, if n is 1, then n minus 1 will become 0. So you'll get this as 0. All this is good. So this is how the different, how you'll handle for each and every value. And now um, we will return this good paths at the end. And the thing that's left is the union point. So this is a typical data structure. I don't know if it's already provided somewhere as a library, but we can just quickly code it up. So we'll have like a parent array. So obviously we'll have few things. We'll have an and, we'll have a parent array, and we'll have a size array. And let's have this constructor. And the constructor will say this dot n equals to 1, and it will create these two arrays. So it will create a parent array, and it will create the size array, size for the size of the component with this guy as the root, right? That's that sort of a thing. Or size of the tree with this guy as the root. So now what we want to do is for each int I equals to 0, I less than n, I plus plus. Well, so parent of I is set as I, and the size of I is what you set as 1. All right, so now we are going to implement two functions. One obviously is the find function. So find me the component for this x, and other is a union function which says, hey, join this x and y, right? So what do we do in find? We want to return the ultimate root of this. The way to return the root would be while parent of x is not equals to us. That means it has a further parent. Then you go x equals to parent of x. And we want to do path compression. So we can also do parent of x equals to parent of x. This will help to do some sort of a path compression, which improves the time complexity. I would recommend you to read about the improvements that basically the weighted uh, union and this path compression that we use to improve the time complexity or of the algorithm. In the union, what do we do? All right, so union, we want to find the root. So we do root of x equals to, we find x, and root of y equals to, you find y. And now you connect this root of x and root of y, but which becomes the parent? And this is where we use weighted union find. So if the size of root of x is greater than the size of root of y, so you want to add a smaller child to the parent. So then you do parent of root of y equals to root of x, right? And then your size increases by, uh, all right, we called it size, we called it size. And this is where we are doing weighted, that is add smaller tree as child to larger tree instead of the other way around. So size will increase by the size of the child, and if the x was smaller, so x has to be added as the parent, sorry, as a child. So parent of Rx will become Ry, and then size of Ry is going to increase by the size of x. And this is our union find. Ultimately, we then, yeah, we don't have to return anything here. Here we had to return x. All right, so that's our entire logic. Now let's run the code and fix any compilation errors. And there are a bunch. So line number 2, class is just like that. Line number 69, Mr. Semicolon. Let's fix all other errors. All right, the test cases are accepted. Let's submit. And it gets accepted. All right,